Hello everyone, this is a live stream BANA 3000 Operations Management Week 2 Lecture 1. And this week I will cover the definitions and get started with the material, and also material for Homework 1 coming up next week, due on September 6th. So we have 2 weeks for this material just to ease into it. Today I'll do definitions. And then on Wednesday I will cover the homework for the definitions. And then next week I'll go into quality analysis a little bit, quality control, and then next Wednesday talk about the homework. Okay, so I do have a chat room, and this is a lecture, and if you have any questions, you can just post it here on the chat room, and I'll answer them if I can. And let's bring up the syllabus. In the syllabus, if we come down here, here we are on August 24th, the definitions and quality control. As I say, this week I'll do the definitions on Chapter 1 in the Red Book. And then next week I'll do quality control, the second half. And then this is the Monday live stream. And then Wednesday is when I talk about the actual homework, on how to work the problems and where to find the answers and this kind of thing. I don't work the problems for you, but I'll work them to the answer, then I'll stop and let you finish it. Okay, now let's bring up Canvas. And in Canvas, notice I have down here, I have the homework already posted, the questions here, and they're not due till September 6th, so you have plenty of time to look at them. Here's the live stream, and I see I have a few people watching, and then the Zoom link is going to be here. So this is definitions and quality control today. Okay, and notice that I'm easing into this. Week 1 was just introduction or the syllabus on where to find things and how to get started. Today I get into the material. Okay, so the material is found up here in the Red Book, and so if we bring up Chapter 1 in the Red Book, Chapter 1, Introduction, Operations Management. And the videos, let's bring back up here in the my website. You click the website, and then you go to Operations Management tab. Okay, we see here on the introduction, this video 1. This is going to be the introduction to operations. And then there's a break-even analysis, which I'll talk about today. And then down here, under process control, this first video will, and also these videos will talk about statistical process control. But what I will be doing here is just to make just a simple introduction to the quantitative aspects, but I'll also be talking about process control charts in more detail. And that's usually this first lecture, this first video. Okay, now let's go to the Chapter 1 in the Red Book. And this is Chapter 1, Operations Management, and that first video. Okay, first of all, operations can be described as a transformation of inputs to outputs, where the inputs are the resources like facilities, like plants and warehouses, and material. That's the inventory, equipment. These are like the machines, and then finally labor, and these are people. Those are some of the inputs. In this course, we will emphasize material for a couple of weeks. We'll emphasize equipment and labor in aggregate planning, and the output is products and or services. And the products and services usually go together. Some more products and services, some more services and products, but rarely do you have a pure service industry. You'll have usually a combination of the two. So under process, under the operations, you can design operations to do what you want to do, manage operations to make sure that you maintain a production level and quality that you want, and control. In control, what I mean by control is change and updating and modifying, and changing operations today to respond to things that happen that are not expected or that are expected. Okay, Now, in order to emphasize this or enhance this, we have different levels of functions or analysis or decisions. So you'll have something called strategic functions or a strategic analysis or strategic decisions, and these have to do with long term. And the long term have to do with things that are happening 5 to 10 years to even 15 years into the future. And so those are strategic analysis and strategic decisions. And there's where you have design, but also you have control on how things need to be changed when things change, when industry changes, when technology changes. How do you change with it? The next is tactical. Tactical is medium term, and medium term has to do with planning. How do we plan things from a day-to-day basis? And there's where your management comes in. You say management is how much inventory do we need? How much production are we going to produce this quarter? How many people do we hire this year? And so depending on the design and the management of your operations, there's where tactical functions, tactical decisions, tactical analysis come in, and that's more planning. The last is detailed operations, and these are day-to-day operations. Day-to-day operations where how to make things efficient, how every day things are efficient, quality is maintained, and you continue to produce high-quality, efficient operations. Okay, next is industries, and there's different kinds of industries. I've only divided this down and aggregated and generalized it to only 3 types of industries. There's a lot more than this, and there's some that are not here. But these are the 3 we'll be looking at for operations in this course. First is continuous operations. And continuous operations have to do with doing the same thing over and over again continuously. And there's different versions of this continuous operations. Some continuous, and the video will go through this in detail. So I highly recommend you watch the video. The continuous operations could be manufacturing, could be repetitive operations, could be all different things. And we'll talk about the strategies down here in just a second. The second is intermittent. The intermittent industries is a combination of the continuous operations where you have, let's say, assembly line and production, but then you don't produce just the same thing all the time. You shift it over to a different product line. So the textile industry is a good example of different product lines. Okay, and finally the service industry. A service industry is defined by when the customer is part of the operations. That is a good definition of a service industry. And we'll look at different kinds of service industries down here in operation strategy. Finally, we have different objectives that we'll be looking at in here. First is monetary objectives. This is where we will start. Maximizing profit, minimizing cost. We'll start with monetary objectives within operations. Then we'll move to a second objective, and that is time. Well, we can minimize our cost and maximize our profit, but let's do it faster. Let's do it with a high quality is doing it in a minimum amount of time. And the third is quality. Well, here we have to define what quality is and then optimize it. So you can have a low cost and a very high minimum time, but you want to maintain a certain quality level within those operations. And so these are the 3 objectives we'll look at in this course. Now there's others, but these 3 we'll focus on. Okay, this is the big picture. This is the overall input-output process that we'll see over and over again throughout this course. As a matter of fact, the input-output process I'll repeat as we go through every topic. Okay, that's the big picture. Now let's go a little bit deeper and let's look at strategies. Well, operation strategies, the way I define strategy for this course is a series of decisions that lead to an objective, and that objective or goal would be the strategy. So the strategy is the series of decisions and the actual objective or goal. And so the operation strategy is a series of decisions. Well, in operations, I'm going to introduce this by looking at 3 operations decisions: a product design, a process design, and an inventory design. Now remember, each of these are decisions that are made around design. First, product design. You can design your product as a customized product or a standardized product. And again, the video gives some examples of customized and standardized. Well, in here to explain it, and this is an explanation. The videos are presentations. This is an explanation. In the presentation, the videos, I give examples and presenting it. Here I'm explaining it. And then on Wednesday, I will apply it. Okay, in the customized product, these are products that are designed specifically for one customer or a very select number of customers. A good example of customized product design would be the O-rings for the space shuttle for NASA. Okay, another customized would be custom homes for specific clients. Another is custom clothing. You make clothing for a very specific customer or a very specific company. You have uniforms, would be customized type products. The other is standardized. And standardized, I guess using the same idea of definition, is you have one design and one type of product for everybody. It's standardized for everyone. Well, sometimes standardization is required. In other words, you'll have standardized food quality. The Food and Drug Administration will have standards of food, will have standards of medications that have to be met. Okay. The other standards are like legal standards. You have to meet certain certification standards or certain requirements within an organization in order to meet health, in order to meet maybe logos or different economic or legal standards. So standardization of products, sometimes they're required. Okay. And so, but in product design, usually you'll have a combination of a customized and standardized within one product. So a good example of that is the computers. You can design a computer for a very specific function, but every component in that computer could be standardized. In other words, it meets certain standards. For example, the input energy standard, or the monitor standard, the output resolution standard. So you'll have standards, but the way you do that internally could be very customized for a very specific product. You design a computer system for processing, design a computer system for graphics, design a computer system for music or art. Okay. Next is a process design. Now, where here you're designing the product itself, here's the process in producing that product or the process in generating that service. So we're going to have two branches of process design. We'll have a process manufacturing design and a process service design. So the two types of designs and processes, manufacturing and service. Under manufacturing, we'll have something called a product-focused manufacturing process design and a process-focused manufacturing process design. Here's the difference. A product focus says, okay, an example of a product-focused design for manufacturing would be an assembly line. When you think of an assembly line like making automobiles, they're going down the assembly line. Well, the process design, the design of the process, is focused around the needs of the product. And so it's focusing on the product needs. Well, the product needs to first do the chassis, then do the body, then do the engine, then do the wheels. And so this is the order in which this product needs to be processed, need to be developed. And so you're focusing on the needs of the product. And that's an assembly line or a conveyor belt. Okay, and so that's a product focused. Well, the characteristics of product focus is you can make a very large quantity, very efficiently, very fast, very efficient, and low cost. Because you're doing the same things over and over and over again, it creates efficiencies as far as speed and cost and high volume, low cost in your products. So there's the characteristics of product focus, which I say in the video. The second is process focused. You say, okay, well, I'm not focusing on the needs of the product, I'm focusing on the needs of the process. Well, if you're producing something, if you're making a table, you're going to cut the wood, you're going to sand the wood, you're going to varnish the wood, you're going to assemble the wood, you're going to package it. But then an example of process-focused design is something called a job shop or maintenance shop. In other words, you say, well, I can build these things, but I want to build not just a table. I want to build tables, I want to build chairs, I want to build picture frames, I want to build bookcases. I have a lot of products I want to build, and so I'm going to have a shop, a job shop, and that shop can do different jobs because I'm focusing on the processes. So I'm going to have a machining department, a saw department, a sanding department, and that department is going to have all of all this equipment to do that specific job or part of a job. So if I'm making a table, well, the wood comes here, and I'll do this in this department, and then this department, then this department, then this department. And so that product gets shipped around to the different departments before it comes out as a finished goods. But what if I wanted to make a different product? I would go to a different series of products because that design is focused on the process. This process, well, the characteristics of process focused, those characteristics have to do with you can have a variety of product offerings. So product variety is a characteristic. And since you have focusing on the process, then that process can be done extremely well. And so usually quality has to do with process focus because you have the best people doing that process. On an assembly line, you'll have people spread out, but you'll have in a job shop, in a process focus, then that job shop is doing that process as best as it can. So the high quality, so high quality product variety. Usually those are the characteristics of process focus. Now, just as these designs can be combined, these designs can be combined for manufacturing process design. Oh, and also be very careful here, guys. Notice this is a product-focused process manufacturing design. So it's not my terms, it's industry terms, so be very careful. This is a process-focused process manufacturing or manufacturing process design. There's a lot of things floating around. Make sure you understand what's hyphenated and what's not. Okay. The combination of these can be done all different ways. One of the most common and popular combination of product focus and process focus is something called cellular manufacturing. Now let me put it here. Cellular manufacturing. And here's where you create cells. And cells are very common today, and they started back in the 1980s, 1990s, last 20, 30, 40 years. But they're very efficient today. They're very good. You create a cell. Within that cell, you are going to have a product-focused design within the cell. So the example is that, well, that product focus is not high volume, low cost. The product comes in, and you're only making part of the product. You're only using a cell, and that cell might use one or two different departments as a job shop. And so you have high quality within that cell. But you're not making the entire product. You're only making part of the product, a component, or just part of an inventory. And so you have high volume, low cost, very fast. But then the way you put the cells together then is how you're going to make the product. And so there you have product variety and you have quality. And so a cellular is a combination of product focused and process focused. Okay. The other type of process design is a service process design. Well, remember, I define service industry as when the customer is part of the operations. Well, the amount of customer involvement in the operations to find different types of service designs. So again, this is a service process design. Well, there are three types: quasi-manufacturing, customer's participant, customer's product. Well, quasi-manufacturing is a service design within an operation where the customer has very little to no input or contribution in the process. It's a process design, but it's quasi-manufacturing because it's part of a service design, but it's part of the service where the customer has very little involvement. An example: you go in and order something from Wendy's, and you order it from Wendy's, and they go, "I want this hamburger," and so you give them the order, and then once you place the order, then you move over here, you wait for them to put the order together. Well, when they're putting the order together, that's quasi-manufacturing because you're no longer involved in the service. The service is separate from the customer. It is actually creating the product then. Now, when you gave the order, you are participating in the service, and that's customer as participant. You are participating in giving the order. So you have the server listening, you have the customer giving the order, and so there's a coordination there. There's a communication. There's a participation between the server and the customer. Okay. In consulting, you have a combination of the customer and consultant, and that's customer as participant. And then, so notice the requirement, the labor requirements here. For quasi-manufacturing, you need someone who does a task extremely well and repeat it, very little error. Customer as participant, and when you're giving the order, you need a server who's very good at listening, who can communicate. If you don't understand them, or you're not patient with them, then that person probably shouldn't be on that part of the service. Because some people are very, very good at routine tasks. Maybe they should be quasi-manufacturing. They're not very good with talking with people. They shouldn't be in the front taking orders. But some people are very good at communicating. They understand, they communicate well, they take the orders well, but they're not very good at doing routine tasks. So you're going to separate the labor out in the service process design on the quasi-manufacturing and customer's participant. Now there's all different types of flow and requirements, and so these are just two. Quasi-manufacturing, you have routine tasks. Customer as participant, you have engagement in the customer, or engagement that's very well done by the server. If you've ever worked in retail, you know what I'm talking about. Sometimes it's very difficult understanding what people mean, what they say. Because people will say things, they don't necessarily mean what they say. They mean something that they're not saying. So you can't hear what they say, you have to hear what they mean by what they say. Some people are very good at that, and some people are not. And some people are patient, some people are not. And so the whole idea of service design is make sure that you put people where they need to be. The last is customers per product, where the customer is the product of the service. A good example of this is a medical field or a salon where they do your hair. You are the product. And so the whole idea here is what's quality? Quality is the customer is happy, satisfied with the service. Up here, the service has to be done in such a way that it achieves an objective. Well, the objective down here is the customer is satisfied because the customer is the product. So the definition of quality is different with customer as product than customer as participant, for example. Because the customer is participant, but if they don't get the product the way they say, they're going to be upset. But down here, they are the product. And so they have to be satisfied, even though it's done right. If they're not happy, then that's not necessarily high quality. And so here's 3 different levels of involvement of the service. The final is the inventory design. And we have 2 types, make to stock and make to order. And this is finished goods inventory, or FGI, or inventory design. Now make to stock means you're producing, here's your product up here, product design. Here's your process in making, let's say manufacturing process design, and making the product. But then what's your inventory design? Well, make to stock says, I'm going to make this inventory, I'm going to make these products to create inventory, to create stock. Stock and inventory is the same thing. I'm creating my stock, my inventory. And my demand is met out of my inventory. So I'm making it to create stock, and demand is made out of my stock. Now a make to order is different. A make to order says, I'm going to wait until I get an order. Once I get an order, I'm making it to satisfy that order. In other words, a pure make to stock has no inventory. So they're making the product to satisfy the order. And so that's a pure make to order inventory design within operations. Now, an example of make to stock would be an inventory of bread in the supermarket. You go to a grocery store, a supermarket, and you buy bread off of out of the inventory, because they've baked that bread, they've packaged it to create inventory, and you're the customer, so your demand is met out of the inventory. Now make to order, an example of this would be like Dell computers. So you call and say, I want this, and this in my computer system. Oh, you want this CPU and this hard drive and this monitor, and they put it together and then ship it to you. So they're not making the product or assembling the product until they get the order, and they assemble a product specifically for that order. A good example of make to order is Amazon. Now they don't make the products, but they put the order together and ship it to you. And so that's assemble to order. Okay, they assemble the order and then ship it to you. Okay, again, these can be combined. And these can be combined within the supply chain in the way the make to stock, let me go ahead and type it in here. Make to stock is called a push system of operations, of inventory. You're pushing the inventory downstream to the customer. Now make to order is referred to as a pull inventory strategy, where the order is pulling the inventory out of the system. So where the push meets the pull, that's called the push-pull boundary. And so you'll have push systems and you'll have pull systems, and where that push-pull boundary is in your operations is your inventory design. And here's your combining the two. For example, let's look at the push-pull boundary of a compact computer. And they have these computers that say, you can buy this laptop, but here's our inventory. Well, the inventory is in the store, like a Best Buy. You say, I want this, I want this, I want this. Okay, well then the push system, the pull system and the push system, the push-pull boundary is in the retail store. Dell Systems come along and say, you know, I want to take that push-pull boundary and move it deeper into the supply chain. I want to have the pull system at the component level. The push-pull boundary is not at the finished goods level, it's going to be at the component level. And so that pull system goes to the components are put together to create a product, and then it's delivered. And so the push-pull boundary can be the primary design of a brand new company. You have a different push-pull boundary in your supply chain, and now you have a brand new company. A whole different approach to delivery. Barnes & Noble, they buy book at the Barnes & Noble store. But then Amazon says, you know, I'm going to deliver it upstream. I can put an order together and mail it to them. And so it's online. So the idea of a push-pull boundary is strategic, and that could be part of your operation strategy. So how you produce the product, how you create the product, how you deliver the product, Those are the three different decisions, and how those decisions go together create your operation strategy. 100 years ago, 80 years ago, after World War II in the 1950s, the operation strategy was very straightforward: mass production. In other words, they had very large factories, because in the United States we had a lot of factories shifting from wartime production to peacetime production, and so that manufacturing started creating very large amounts of product. Economies of scale drove down the cost, and we captured markets. Japan, after World War II, did not have a large capacity because when they shifted from wartime to peacetime, they didn't have the capacity. The capacity was pretty much gone, so what they had to do is they didn't have that much of a push system. They had more of a pull system, and they had to back up and talk about our product design, our process design, and even services have to be more of a pull system than a push system. The United States went to a push system: high volume, low cost, capture markets with mass production, economies of scale. But then other countries went to more of a pull system, and they looked more at quality, because pull systems and process focus had more of a quality, and so then they began combining the two. Well, today the supply chain has a combination of push-pull boundaries upstream and downstream. It's becoming much more sophisticated, and that's why operation strategy 100 years ago was pretty straightforward. Today it's much more complex, and the operation strategy applied to the supply chain is called supply chain management. And we don't get into that in this course. We'll just look at just operations. But the way operations deal upstream and downstream is supply chain management. That's a different subject for a different course. Okay, that's the qualitative part. Now here comes the quantitative part. Now in the break-even analysis, here is where I am moving to mechanics, to looking at calculating and quantitative analysis. I start with break-even analysis because we use break-even analysis over and over again in different places throughout this course. And so break-even analysis can be applied to different things. And here we're talking about production. It can be applied to different things all the way through. Okay. But I'm taking this as an opportunity to introduce how to do quantitative methods within operations. Now, the reason I say that, a lot of times people, especially from high school, are not well prepared for business. I mean, let me just say that. I don't think so. This is my opinion. This is opinion corner. It's not well prepared. They're taught how to solve this thing. They're taught how to think. They're taught how to memorize. And you get in industry and you go, I don't know what to do. What do I do? Well, you figure it out. Oh, well, how do I figure it out? Because tell me what to do. No, you have to figure out what to do. And so you have to think. And that's why at a university, the most important thing we do here, one important thing we do, is not what to think or how, but we teach how to think. And that's what I'm going to do. That's what I'm going to be doing here with break-even analysis. How do you solve problems? Okay, here's the problem. 3 production processes: automated, product focus; cellular, combination of product focus and process focus; and job shop, process focus design, have the following cost structures. We have a fixed cost that is just there whether you produce anything or not. It's a fixed cost to this operations. And then you have a variable cost. When you start creating things, you're going to have a variable cost of production. Okay. Now, even though these numbers are not necessarily accurate in magnitude, the ordinal relationship is relatively common. It's reasonable. Automated usually is much more expensive to set up because a lot of setup, but it's cheap to run, high volume, low cost. A job shop is cheaper to set up because you just have all the equipment in one place. You don't have to put an assembly line, but it's more expensive to run because you're moving it everywhere. And cellular quite often is in between. The fixed cost is between automated and job shop, and the variable cost is between the other way. Okay, now I said it's a break-even analysis because I'm saying which one of these will have the lower cost. So it's a cost analysis. It's only part of the decision, which process do we use? Automated, cellular, or job shop. So part of that decision process is cost. So how do we analyze the cost? Well, at the top up here, it's break-even. So when we look at this, what's the break-even analysis? Well, how do we know that this is a break-even analysis? Before we start calculating it, let's stop and say, is this a break-even analysis? Yes or no? Good question. Years ago, I was teaching this in class, and I had a student raise his hand very quickly. He says, oh, I know how. Oh, okay. Before I go, okay, how do you know this is a break-even analysis? And the guy was being funny. He says, oh, it's very, very simple. All you do is you look up here and it says break-even analysis. It tells you. And the class kind of chuckled barely. And then I said, oh, okay, yeah. Well, you know, when I went home, when I was driving home, I thought, that's very significant. That's very true. That's how it's taught, say in high school and in some undergrad. And some courses, people teach it that way. This is a break-even analysis. Here's how you solve it. Well, I guarantee you that these problems don't come with a title in industry. This is a business school, a professional school preparing you for profession, to be a professional out there. When you start working out there, they don't come and say, work this problem. They say, what's the cost? Oh, I have to, one, recognize that it is a break-even problem before I solve it. Okay? So the first thing is the definition. Is it a break-even analysis? Now, I'm going to do this in two ways. Okay? Well, another quick story, and that is, I wanted to emphasize the point to recognize what kind of problem it is. I wanted to recognize it. I taught this at another institution a long time ago, and I wanted to emphasize this, and I was talking about a technique that we're going to be doing. Let me bring back up the syllabus real quick. Down here, MRP. Okay, I got to MRP, which is Manufacturing Resource Planning. I got to that technique, and so I came in. It was like a 2-hour lecture. This is years ago, and I said, well, today we're going to do a simulation. And so I set up a production process, and I said, okay, I want you to optimize this production process. You're going to be this, you know. So I said, tell me what I do. And they go, oh, I have no idea. Let's see. And so they try to create a production plan, and I had an inventory manager and production manager and flow manager, and so the first one tried it, and we simulated, and it didn't work. They go, oh, dude, okay, I ran out. Okay, well, then you try it. And so they learned from each other and tried it. And at the end of that class period, everyone failed because they tried to solve this problem and they couldn't solve it. Interesting. And I kind of saw everyone kind of like, oh no, maybe I shouldn't be. These were majors. These were operations majors. Maybe I shouldn't be in operations, you know. I said, you know, before we leave, we're going to do this again next week or the next class period. But before you leave, let me show you something. I'm not going to say anything. I'm not going to say anything at all. I'm going to take this problem and rewrite it on the board. So I did. But I took the problem as I described it, and I rewrote it on the board, and I rewrote it according to the MRP design. I put it in an MRP framework. When I did that, I saw the light go on everybody in the class. Go, oh, this is an MRP problem. We know MRP. Why didn't you tell us it was an MRP problem? Why didn't you tell us what kind of problem it was? then we can solve it. I says problems don't come with titles. And so then we say class dismissed. We're going to do it again next week, or the next class period. It was another class period. So when we came, I put it up there. Everyone knew what kind of problem it was, and they go boom, 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 boom. I made it more complicated. Everyone solved it perfectly. Now, they failed because they didn't understand MRP? No, they knew how to do it. They failed because they didn't recognize what kind of problem it was when it came to them. Recognition of problems is the first step to being successful. Recognize what you have in front of you. It doesn't come with titles. It doesn't come with explanations. It comes with a problem. It says, okay, well, how do I know this is a break-even analysis? We're going to approach this two ways, and I do it in detail in the video. Watch the video. The first one is saying the boundary value approach. Okay, what if I had the production really, really small? Okay, what if I produce nothing next year? Okay, which one of these has the lowest cost? Well, obviously J, because 75 is less than 110 and 80. That's easy. Okay, so the concept is when the production is really, really low, then J will have a lower cost than A or C. Yeah, that's true. Okay, fine. Let's go, whoops, sorry. Let's go the other extreme. What if I produced a very large amount? Produced more than I would ever produce. Okay, there's a huge production. Let's say 1 million. Okay, let's say if I produce 1 million, then this is going to be $2 million variable cost, right? 2 million plus 110, that's going to be the cost. This is going to be 4 million 80. This is going to be 5 million. Now which one is the cheapest? Oh, A is the cheapest. 2 million is less than 4 or 5 million. That's right. But I'm never going to produce that much. I'm never going to produce zero. I'll never produce 1 million. But wait a minute. Very low production, J is the cheapest. Very high production, A is the cheapest. Since they're different, that's an indication that somewhere between 0 and 1 million production, the cost is going to be the same, and that's the definition of break-even. At what production do these costs come together? So low production, I'll go with J. High production, I'll go with A. What about C? Well, let's back up. Then let's look at C and J together and A and C together. Because I know there's a break-even. Because the cost of low and high, the boundaries are different. So somewhere between those boundaries are the same. The second is the structure of the problem. When the fixed cost decreases, 1, 10, 80, so when the fixed cost decreases at the same time the variable cost increases, when one goes down and the other goes up, that structure of the problem, there's a break-even in there. Aha. So that structure is something extremely helpful to know what you're looking at, to recognize that the structure indicates there's a break-even. Let me illustrate this. Suppose, let's take this here, and let's come up here and do some stuff here. Suppose that, let's take this and let's make it gray. Did I do it? No, I didn't. Let's make, oh, that's the wrong thing. Sorry, this right here. Let's make this gray. I got to highlight it again. Okay, there we go, gray. And let's reverse these. Let's assume this is, oops. Let's go back to dark. There we go. Let's assume that this is 5 up here. This down here is 4. And this down here is 2. Okay. In other words, I'm reversing these. I'm making this 5 up here and the 2 down here. So now, when you look at this, which one has the lowest cost? Well, the lowest cost on fixed cost is J. The lowest one on variable cost is J. So which one is the lowest cost? J. Does it matter what you produce? No, it doesn't matter. J will always be lower. So there is no break even. Okay? And in the homework, you're going to see a device that I'm using called Roger. Now, Roger will come up and say things that are wrong. And they'll be in the homework. And it says, which one of those things that Roger said was, and Roger will say right things, correct, but he'll say wrong things, incorrect. And I say, Roger's saying 5 things here. Which one is wrong? You have to pick it out. Very interesting. Because do people say wrong things all the time in industry? Yes. Got to be careful. If they say something wrong, you don't want to make a decision on something that's wrong. You have to question. You have to question what people say. Okay? Listen to what they say, question what they say, and make sure that you understand what's going on. For example, suppose you're a consultant and you go into a suppose this is what you have here. You're a consultant, and so the consultant says, you know, could you do a break-even analysis for us? Oh, okay, yeah, sure, I know how to do that. Okay, this is my problem. Could you come back and tell me what the break-even is? And you go, and so you go look at this, you go, and you get ready to say there is no break-even. The answer is J. You don't have to pay us, or you don't have. The answer is J. And so Roger says, yes, we can. Yes, we can. We will give you an analysis. And they go, no, there is no analysis here. There is no break-even. J is going to be the lowest cost always. So if Roger says we can do it, and then go, okay, we want you to give us analysis of the break-even. And we're going to expect the production where A is cheaper, C is cheaper, J is cheaper, and that doesn't exist with this problem. So Roger's going to get you in trouble. You came back, oh, you took the money, but then we didn't do it because that answer doesn't exist. Well, why did you take the money then? Oh, okay, because you didn't listen to what Roger was saying, and he was wrong. My point is, know what you're looking at. Know what can be done and what can't be done before you start doing it. Do people try to do things that can't be done? All the time. Okay? Do people ask you to do things that can't be done? All the time. Recognize what can be done and what can't be done. Again, this is a professional school. It's not just working problems. It's understanding what the problem is, if it is a problem or not, and then how you can come up with a solution or an approach to that problem. Okay? So let's go back. There we go. No, one more. There we go. Well, that's recognizing that it is a break-even. Now, how do you solve it? Okay. Well, I'm going to do this 2 ways. The first is logical. I call this back of the napkin approach. Before you start doing the arithmetic, and a lot of students have a very hard time with this. They say, "What's the arithmetic? What do I multiply and add, divide, and subtract? What do I do?" I say, "Wait a minute. Before you do that, understand the problem." Okay, here's what I mean by that. Let's look at C and J. We want the break even between these two. Okay, right here, extreme value. If I produce nothing, then which one of these? Well, J is cheaper. By how much? By $5,000. Okay. But when I start producing something, then J is $1 more than C, right? So initially I have $5,000 cheaper for J, but then J is $1 more. So how much do I have to produce in order for C and J to have the same cost? 5,000. Because if I'm saving $1 here, then I'm saving $5,000 after I produce 5,000, and then the costs are the same. So the break even between these two is about $5,000. So 4 times 5,000 is 20,000 plus 80 is 100,000. 5 times 5 is 25. plus 75 is 100,000. The cost is the same. So between these two, 5,000 is about the break-even. Well, I made these numbers towards exactly the break-even, but you don't need to know exact. You just round numbers. It's somewhere around 5,000. 48, 52, 51, 46, somewhere around 5,000. Therefore, very low production, J is the cheapest. How low is low? Below 5,000. If it's above 5,000, C would be the indicator of a lower cost. Okay, let's do the same with A and C. Well, the difference here between 80 and 110 is 30,000. I'm saving $2 per unit. So how much do I produce it to where those costs are going to be the same? Well, half of 30 is 15, so 15,000. So now I have a rough idea of the break-even between A and C is 15,000 units. C and J is 5,000. I have a good idea of what the answer is. So I understand the problem before I do the arithmetic. So the second is arithmetic. And let me just say, the arithmetic should validate your understanding of the problem. Okay, well, initially, when you're first learning this, a lot of times you don't have a good feel for what the answer is. But if you're in industry, you're doing this over and over and over again, then you do have a feel for what the answers are. And when those numbers change, you get a feel for what the answer is. And this arithmetic should validate those answers. It'll give you the exact answers, but they need to correspond with your understanding of the problem. The understanding and the arithmetic, the validation has to be together. Now, if the understanding doesn't match the arithmetic, then maybe your understanding is wrong or the arithmetic is wrong. Okay? So here's how to do it. Well, between A and C, I bring the fixed cost down, fix this here, fix this here. I bring the variable cost down times X, 2X, 4X, solve for X, and I got my break even. And I'll do this more on Wednesday. Again, between C and J, I bring the fixed down, I bring the variable down, solve for X, I got 5,000. Notice there's 5 and 15. Now, if these numbers don't exact, you get a feel for generally what the answer is, in general. And so these might not be exactly 5 and 15, but they'll be close. So you get the understanding of the problem, what the answers should be. Down here, you get the validation of that and the actual values. So you're validating it. Sometimes when I'm working on Wednesday, I'll be working this real life. I'll be working this and go, wait a minute, this doesn't make sense. This doesn't feel right. I back up, and sure enough, I made a mistake somewhere. Okay? When you start doing computation, are you going to make mistakes? We all do. We're human. How do you catch them? You get a feel for what the problem is before you do the arithmetic. Get a feel for it. Oh, yeah, it's about this, yeah. And then when you do the numbers, those numbers should correspond and correlate and validate and go hand in hand with your understanding. Yeah, that sounds right. That feels right. I keep saying feeling. When you're working with numbers, feeling is important because you get used to what those numbers are saying. Numbers are just a picture of reality behind those numbers. You get a feel for that. That's the right picture. It's not the wrong picture. It's the right picture. And the numbers should bear that out. So here's the definition. Here's a solution. And finally is the representation of the presentation of the numbers. And I'm going to use a graph here. You can represent this different ways. I can use it graphically. Okay. Well, what if my production was 0? If my production was 0, then again this goes away. It goes away again, and I'm just looking at my fixed cost. 75K, 80K, 110K. 75K, that's my J. 80K, that's my C. 110K, that's my A. That's my dash. I have a dotted, solid, and dash. Okay, let's bring this back. And then when I start producing, I'm going to add $2 per unit to A, $4 per unit per C, $5 per unit for J, And so these are the slope, that's the slope of the line. I'm adding 2, 4, and 5. Okay, so for A here, here's my $2, that's the slope of that line. Here's the $4, that's the slope of that line. Here's the $5. You can see where they cross. They cross right here at 5,000. That's what I expect. That's what we expect, right? These two cross here at 15,000. That's what we expect. Feels right. This looks good. Okay, the numbers look good. I understood it to be pretty much 5 and 15. I calculated 5 and 15. I graph it. I see that it's 5 and 15. It all corresponds. It all correlates. That's how you work quantitative problems in business. You do it multiple ways, and they all should come together. And if they don't, there's something wrong somewhere. Go back and find out where it's at. Well, graphically, this is a good way to present it, because not only does it tell you what the answer is, these two, here's the break, that's what I mean by break even. These two here cross at 5. These two cross at 15. But also you can say, if you're doing A here and you're producing 5,000, this is how much more expensive A is going to be. If you're producing, let's say, 15,000 and you're using a job shop, here's how much more expensive it's going to be. So not only does it tell you what the answer is, it tells you what the costs are if you deviate from that production. Because usually production varies. It's not exactly 5 or 15. It varies every year, every quarter, every month. And so if you deviate a little bit, you can see that if I go with a C here, you can see how much more C costs if it's less, how less C costs if it's more. Okay, between 5 and 15, C is the cheapest. Less than 5, J is the cheapest. More than 15, A is the cheapest. Okay, well, this gives you a good feel for what's happening as production moves around. Okay, so the presentation helps with the understanding. So the question is, which one's the cheapest? Which one has lowest cost? Well, it depends on what the production's going to be. Well, how much we're going to produce? Well, that depends on what the demand's going to be. How do we know what the demand is? Well, that depends on your forecasting analysis. So to answer this question for the company, this break-even analysis has to be matched with a forecasting analysis. And the forecasting analysis is what we're doing in the next topic. But before we go to the forecasting, next week we'll be looking at quality control. Embedded in this, quality control. Well, do we produce it in-house or do we produce it out? Do we outsource it? Outsource to a third party. And that's what we're looking at next week. But this Wednesday, we're looking at the homework and the quantitative part through the break-even analysis. That's how we're doing on the homework. Next week, we'll do quality control, and then we'll do the homework next Wednesday on the quality control part of the homework. So that's what we're doing. That's where we are. Okay? And that's pretty much the lecture for today. Okay? I see I have a chat room again. No one asked any questions. I hope this really does help. I hope there's no questions because it's clear. And if you have any questions, you can bring them up on Wednesday. If you have any questions, you can bring them up in the Zoom. So let's look at the syllabus again. Okay, here we are. The Monday live stream is a lecture. The Wednesday is a lecture for the homework. And I'm starting with half of it, which is the break even. And then Friday is a Zoom, which is office hours at 7 p.m. These are recorded. Oh, by the way, these would be recorded. Let's go to Canvas to finish up here. And see how these are right here, these links to a video. Down here on the definitions and quality control, there'll be 2 links right here, Monday and Wednesday lecture. They'll be right down here for the homework. Here's the homework. You can start working on it. And don't submit it only when you're done. So download this Word file. Boom. Click it. Download it. Open it up. Boom. Enable editing. Enlarge this thing. And there's the homework questions. So work on the homework questions. I think it's 1 through 8. 1 through 8 is this, and then 9 and 10 is going to be quality control. We'll do that next week. So there you go. So we have these first 2 weeks. I'm starting slow, starting nice and slow. Next week is a little bit more in forecasting. Next week is even more in aggregate planning, and then I get into inventory, and then I start decreasing. So the amount of work is kind of like a bell curve. It's really slow, and then I increase, and then I start decreasing again, and then we have our exam and project. Then I shift to you doing your work, studying for the exam, and putting together a project at the end of the course. But once I get toward the end here, I'll be talking about that a lot more. That's all I have for today. On Wednesday, tune in for the homework. On Friday, tune in for the office hours and questions and answers. And you can have a link of this video on Canvas. That's all I have for today. Between now and the next time we meet, be safe. Don't take anything for granted out there. Be extra safe so that you can be here and keep learning. And so take care of yourself. See you later.